Hello and welcome back to Physics Galaxy, and this is lecture number 6. And today we're going to study the boundary conditions and uniqueness theorem regarding the Poisson's equation, that was del square V equals to minus rho or epsilon naught. And as we know, this is the second order differential equation. We have to specify the boundary conditions to find the solutions. Okay. Now it turns out we can use two types of boundary conditions. Okay. So two types of boundary conditions we can use. Two types of boundary conditions. One is the Dirichlet boundary condition. Dirichlet boundary condition. And the other type of boundary condition that we can use is called Newman boundary condition. Newman boundary condition. Now, what this Dirichlet boundary condition means? So, if we are using Dirichlet boundary condition, we have to specify potential at all boundaries. Okay. So, suppose this is my boundary. Let me draw it here. Suppose, suppose this is my boundary. Okay. So this is my boundary. Now, boundary can be of any shape. Okay, it can be spherical, it can be a parallel, infinitely long parallel sheet. So let's take this as my boundary. Okay, boundaries can be of finite nature or infinite nature. So let's say this is my boundary of some space, right? Then if I am using Dirichlet boundary condition, then that means I have to specify potential at this boundary. Okay, suppose I specify the potential of this boundary as V. Okay, so if this is the case, then I am using the Dirichlet boundary condition. Now, what about the Newman boundary condition? So, if I have to use Newman boundary condition, then if I have some boundary, suppose this is my boundary. Again, boundary can be of any shape. Okay, suppose this is my arbitrary boundary. Then what I have to specify? I have to specify the normal component of the potential. Okay, normal derivative of potential. So that means I have to take dv by dn, where n is a perpendicular component. Okay, so the normal vector n. So this is what I have to specify for each and every boundary. Okay, dv by dn. Okay, so this is the Newman boundary condition, and this one is the Dirichlet boundary condition. Now let's take some examples. Let's take simple examples. Okay. Now before taking an example, let me give you one important theorem regarding these boundary conditions. Is that if these boundary conditions are given, then it guarantees, okay, both. This also gives us a guarantee, and this also gives us a guarantee that the solution that you will get will be unique. Okay, so this will give us a unique solution. Okay, so unique solution. So both these boundary conditions guarantee us that the solution that you will get after solving your Poisson's equation will be a unique solution. Okay, now if it's a unique solution, in case of Dirichlet condition, we don't need to find any solution. But we have to be careful in case of Newman boundary condition, because yes, it will give a unique solution only up to a constant. Okay, yes, it will give a unique solution only up to a constant, additive constant, up to an additive constant, up to an additive constant. Okay, so it will not be entirely unique, but to an additive constant, it will be a unique solution. So that means, if suppose in case of Dirichlet boundary condition, if you find solution V equals to um, uh, V of uh, suppose V of X, suppose this is some solution. Okay, then Dirichlet boundary condition guarantees us that this is the only solution. Okay, and similarly in case of Newman boundary condition, if you find solution, suppose V equals to V of X, then it guarantees that this is a solution, but this solution might have some constant. Okay, plus some constant. Okay, now let's take an example from the Dirichlet boundary condition. So suppose we're using Dirichlet boundary condition. Dirichlet boundary condition. Now, why are we using Dirichlet boundary conditions? So we are using Dirichlet boundary condition when we are dealing with the metallic surfaces. Okay, suppose you have a conducting shell. Okay, then or you have a capacitor. Okay, then we specify potential. Suppose V equals to 0 and V equals to suppose some finite potential. Okay, V equals to V naught. So we're specifying potential at each surface, then that means we're using Dirichlet boundary condition. Okay, so we usually take this type of example, V equals to V naught, grounded conducting shell. Okay, grounded conducting shell, conducting shell. So that means we're using Dirichlet boundary conditions. Okay, so let's solve this example. Okay, it's a very simple example. I have a grounded conducting shell. Okay, I have a grounded conducting shell. That means potential is given, which is equals to 0. Now if I want to find the solution in the inner region, suppose I want to find the solution in this region, okay, inside of the shell and the outside of the shell, what will be the solution? Now you can say that, oh, I have to solve the Dirichlet boundary sorry, this Poisson's equation, del square V equals to 0, because there are no charges, okay, neither in the inside space or in the outside space. And the solution that we know, we can guess, is V equals to V naught, some sorry, some constant which equals to 0. Okay, this is one of the solution because it satisfies this equation. But does it solve the boundary conditions? Yes, it solves the boundary conditions also. Okay, because it's 0 everywhere and on the surface also it's 0. Okay, so if this solves the Poisson's equation, also it satisfies the boundary condition, then that means it is the only solution possible. Okay, that means V equals to 0 inside the shell is 0 and V outside the spherical shell is also 0. Okay, see, using uniqueness theorem we just found the solution. Okay, we don't have to solve the potential. Okay, similarly you can find if you have some V equals to V naught, then what will be the solution? Okay, so the only thing that we have to remember is that this Dirichlet boundary condition guarantees that it is the only solution, unique solution. Okay, you don't have to find any other solution. Now let's come to the Newman boundary condition. Suppose, so now let's take Newman boundary condition. Newman boundary condition. Now why do we use these Newman boundary conditions? Suppose I have an electric field, okay, in some region, and I put my metallic shell, okay, or metal conducting shell inside, then we, in these kinds of problems, we use Newman boundary conditions. So now let's take some example. Suppose in some region, suppose this is my region, okay, where the charge density is constant. Okay, so uniform charge density, uniform charge density. Okay, I'm just giving some example so that I can use Newman boundary condition. Okay, and it is given that the normal component of the electric field at the boundary is 0. So this is given, suppose, let's say E n, okay, or E normal component of the electric field is 0. So that means dV by dN is 0, right? Because electric field is the negative gradient of potential. So if normal component electric field is 0, that means the normal component of the derivative potential is 0. So that means we're using Newman's boundary condition. So if we're using Newman's boundary condition, then we can guess a solution. So one case is V equals to 0. Okay, let's take some hypothetical, suppose, a region inside this uniform charge density space. Now normal component of the potential is 0. So that means inside of this region I have to solve the Poisson's equation, del square V equals to minus rho over epsilon naught. Okay, but without solving this equation, I can use the boundary condition simply, and my guess is suppose V equals to 0. Now if V equals to 0, then it satisfies the boundary condition, because dV by dN will be also 0 and there will be no flux going outwards. Okay, because electric field is 0. So that means this is the solution. Okay, V equals to V naught is the solution, but again we have to be careful because we are using Newman boundary condition. That means it will be correct up to some additive constant, so it can be V equals to 0, which I found, plus some constant. Okay, and this will be the solution for this uniform charge density region. Okay, that V will be some constant.